Welcome to this video brought to you by the Society of Mechanical Ventilation. Basics of Mechanical Ventilation, Part 3. Flow curves and their importance.
Hi, the objectives of our talk today is to define the different flow curves and the factors affecting the flow waveforms and the benefits of monitoring those flow waveforms. The article here in the picture um, is published a couple of years ago by our group, where we try to collect all the information about flow in one place instead of being scattered in the ventilator books and the literature. So what is flow? And flow by definition from physics is the motion of the gas from the ventilator to the patient during inspiration and vice versa from the patient to the ventilator during expiration. In those figures below, on figure A and figure B, A is a pressure controlled mode. You can see the decelerating flow waveform. We'll talk about it a little bit later, where it goes so fast and then decays by time, and that causes the airway pressure to be almost a plateau, and which is A and B, and C is exhalation. D is the point where called maximum inspiratory flow, and E is maximum expiratory flow, and the tidal volume here is like around 600. Almost same patient, same mechanics. But in volume controlled mode, using the square or the continuous flow waveform with the pause here, where the flow is the same all during inspiration, and then again this is a pause, which causing a peak inspiratory airway pressure and a plateau pressure, and the tidal volume is almost the same, but gives you an idea how flow can affect the airway pressure. Those are the five flow curves, inspiratory flow curves that's used in mechanical ventilation. Pretty much the sinusoidal, this one, number C, which is supposed to be close to the normal inspiratory flow while we're breathing normally, but it's not used almost at all. Same with the ascending or accelerating inspiratory flow, also not being used at all. So the most common ones used is the continuous or the square waveform. Again, the flow is exactly the same during the whole inspiratory cycle, and that gives the airway pressure the shape of a triangle almost in a passive patient, and usually in volume control modes only. The descending flow, which again the flow goes very fast in the beginning to the point of maximum inspiratory flow, and during the breath it decelerates down, go down, and gives almost semi-square airway pressure. This also can be used in volume control modes too, and pressure support. Pressure control modes mostly use the decelerating, which you can see a little bit similar to the descending one, just little convex here, and gives like that perfect square shape in the airway pressure. Let's start talking about the expiratory flow first and the time constant. Usually expiration is a passive process due to the elastic recoil of the respiratory system by the kinetic energy which was stored in the inspiration before. Although in some patients who are have an active process, like they're having a lot of dysynchrony or fighting the vent, this process might not be passive. The expiratory flow is dependent on the amount of the applied pressure and the tidal volume. This will affect the peak inspiratory and the peak expiratory flow here. Now the peak expiratory flow and flow time are dependent on the time constant, as we said. And time constant is the product of resistance times compliance. For example, if that patient has a normal compliance of about 70 and resistance about 10, so the time constant is 0.7 second. So each time constant, the flow estimated to decay about 37.8% from its previous value. So for example, here if that peak expiratory flow is 100 liter per minute, after 0.7 seconds, it will go down to about 37.8. Then another time constant, another 37.8 from the previous numbers. So this should be around 14. Another time constant be around 5. Another time constant will be about 1.5 or something like that. So usually you need 4 time constants are required for the lung to reach the resting functional capacity, or the FRC, before the next breath. So if you see in this example, this is the inspiratory time constant, and this is the expiratory time constant in the green arrows. This is with a patient with normal respiratory mechanics. Just this is a person, with low compliance, like an ARDS, and you can see how the inspiratory flow is very sharp and goes down very quick. Same with the expiratory flow is very negative and collapses very quick. You can see the time constants, 4 time constants ends here, and this is basically a pause. Versus this patient, just when you see very slow expiration, so this here is like almost only 2 time constant of the inspiratory phase and the expiratory phase, and we'll show that on the simulator in the next step. Next slide. We'll talk about the expiratory flow and the importance of detecting auto-PEEP, as we talked about in the previous slide. So this is a patient with COPD, and again, as we talked about, you can tell because the expiratory flow is very gradual, slow, and this is a patient on a volume controlled mode, tidal volume 540, PEEP of 5, and he's breathing fast at 31. So we can tell that the end expiratory, again, flow waveforms is not reaching the baseline before the next breath, so this is by definition auto-PEEP. But how much is auto-PEEP? And to say the exact number, you have to do an expiratory pause maneuver. So we'll keep it going for a couple of seconds. And as you can see here, sorry, although we are set on PEEP of 5 here, the real airway pressure after the pause is about 16. So this patient has an extra almost 11 or 12 of PEEP. So this is the way to determine to see if there is auto PEEP by looking at the expiratory flow and putting an expiratory pause maneuver. This is another example of a patient on the volume controlled mode, again constant square waveform. You can see the airway pressure. This is an obstructive lung disease, again as we said, low expiratory flow and very slow decay. And something that's usually missed because the ventilator does not alarm about it is the missed trigger. Auto PEEP in this example, like the previous one, is about total PEEP of about 17, so it's additional 12 of PEEP. So the patient, to trigger the ventilator, he has to exert more pressure, overcome that auto PEEP to trigger the vent. So in this case here, you can see there's this bump on the expiratory flow, like this one, but there is no breath triggered immediately after. So this is missed triggered, missed effort. And it's important because this can be very discomfortable for the patient. And how do we take care of it? We try to get rid of the auto PEEP, whether by decreasing the tidal volume, increasing the expiratory time, try to decrease the respiratory rate. In this example, the patient is actually trying to breathe. If you count, the ventilator tells you that we set the rate at 16. It tells you that there is 16 breaths, but in reality, if you count, this as a breath, like an effort from the patient. This patient is breathing about 25 or 26. So it's very important to notice this just by looking at the expiratory flow. So in this example, this is a patient on a pressure controlled mode. Almost compliance is 70 milliliter per centimeter water, which is pretty normal, and resistance about 9 centimeter water per liter per second. Again, not too high. And I want to concentrate here on the flow again. So this is the inspiratory flow, decelerating one, and the expiratory flow. This is a patient who's passive, does not have any effort. So if you notice in this example, the expiratory flows about minus 60 liters, and so we said about the time constant will be like almost 0.7 second. So exhalation here is almost 2.5 seconds. So that's why almost 4 time constant, and that's why the expiratory flow goes back to baseline or almost zero before the next inspiratory inspiration starts. So I want to see the difference if we make our patient as an ARDS patient with low compliance, see what will happen. As we said in the previous slide, the peak expiratory flow will depend on the compliance or the respiratory mechanics. As you can see here, the peak expiratory flow will start dropping, becoming more negative. In this example here is almost reaching close to 80 or 90. And you can see because the time constant now is very low, compliance here is 10 and resistance is 0.9, so almost the time constant is less than 0.1 second. So you can see the lung tends to collapse very quick here. So just by glancing at this waveform, you can say this patient has a compliance issue, something like ARDS or pneumonia. Let's see the opposite. If we turn that patient into obstructive lung disease like COPD or asthma with high compliance and high resistance, again you'll start noticing the difference. The expiratory flow waveforms should start becoming much smaller. Again, this monitor, this simulator changes the scale, but you can see here it's now almost to minus 20. It was minus 90 before in the ARDS. And you can see the time constant here will be almost 3 seconds. So from minus 20, even after 2.5 seconds, it didn't even reach 1 time constant of the respiratory system. And that's why the next breath is starting before the expiratory flow reaches the baseline here. And that is basically auto-PEEP. So again, by glancing at this patient, you can say this is an obstructive lung disease without making any calculations. The other point I want to show about the expiratory flow, again, that it is dependent on the applied driving pressure and volume. So we'll go to our normal compliance and resistant patient here, and we're just gonna adjust the driving pressure. So let's go up, for example, 30, and of course you would see like the expiratory flow, because the volumes were gonna be higher. So the expiratory flow now again is dependent on the amount of driving pressure and the amount of tidal volume. And something that I didn't say in previous slides, most of the ventilators do not measure tidal volumes, but volumes are basically integrated from the flow waveforms, because so volume equal 1 over flow. That's how the ventilator calculates the tidal volume. Let's talk about the factors that affect the inspiratory flow first in the volume controlled modes. So there's so many factors that affect the inspiratory flow shape and the peak inspiratory flow and the inspiratory time. Those factors are the inspiratory time set on the ventilator, the respiratory rate, the respiratory system mechanics, which is the compliance, resistance, and time constant, the rise time of the airway pressure, and the patient muscle effort, or we call the PMUS. So there's two different ways new generation ventilators set the flow. In the classic volume control, the flow rates are fixed, meaning you set it at 40, 50, 60 liters, so every breath will be the same flow rate, although new generation ventilators, mostly the European ones, can set I to E ratio, and so the flow rate will not gonna be fixed. So in the fixed flow rate, the peak inspiratory flow will remain constant, while the inspiratory time will be variable according to the flow rate. So if you increase the flow rate, the inspiratory time will be shorter, and if you decrease it, it will be longer. And the peak inspiratory pressure will also vary according to the peak inspiratory flow, is a mistake, will vary according to the respiratory mechanics as we talked about. So it will be higher with higher resistance and low compliance. But when the inspiratory and expiratory ratio is fixed, now the peak inspiratory flow and the inspiratory time will be variable, again according to the respiratory rate. So if the peak inspiratory if the respiratory rate increases, the peak inspiratory flow will increase and the inspiratory time will be short, and vice versa. We'll see this in the next slide in the simulator one. So let's examine what we said in the previous slide. This is a patient, again, with almost normal compliance and resistance, and on the volume controlled mode, respiratory rate 15, tidal volume 500, peak of 5. And this ventilator actually do a fixed I to E ratio, so you cannot control exactly the flow rate. Of course, you can do the flow pattern from descending to constant, as we talked about, but you cannot set the exact flow rate. So let's see what happens when we increase the rate. So here in this example, the inspiratory flow is about 22 liters per minute, and the inspiratory time is about 1.3 seconds here. So let's start by increasing the rate, see the effect of the rate. We're just gonna go high, respiratory rate of 36. So of course we're supposed to see the inspiratory time will drop significantly because it's a fixed I to E ratio. It was 1 to 2. Also notice what happened to the inspiratory flow. I think here it's like we're almost 54. So with the increase of the rate, the inspiratory flow went up and the inspiratory time went shorter. Now let's see the effect of the muscle pressure. So we're just gonna go back to respiratory rate here of 20. That patient initially was not working hard, so let's make him more active breathing. So the more the patient actually starting to work harder, and this may be too exaggerated, but you can see here what happens to the inspiratory flow because the patient is pulling hard, that it will go down. So you see it went down from the previous one to here, And of course, you can notice that the patient is pulling really hard on the airway pressure here to the point it's making the inspiratory pressure sometimes negative. And you can see it here, the muscle effort. If you have an esophageal balloon, you will have more appreciation for this. Now let's examine the effect of the change of respiratory mechanics. So we'll make the patient breathe a little bit less. Again, our same patient, he's normal, so let's make him ARDS patient. So we'll worsen the compliance and we'll keep the resistance within the same. And previous example, we said we should see that the inspiratory flow, I'm sorry, we'll just decrease the compliance a little bit more. Here the inspiratory inspiratory flow went down to 30, and of course we can see the expiratory flow went down like markedly negative here in the minus 200. Now let's see the effect of in a COPD patient. So again, we're gonna increase the compliance and we'll increase the resistance, and let's see the effect on the inspiratory flow and the expiratory flow. And again, in this mode, because we're only setting fixed I to E ratio, so the inspiratory flow might not change much. But if we're, setting, I'm sorry, if we're setting a fixed flow, the fixed flow rate is not gonna change much in the inspiration. Sorry about that. Now let's examine the same factors on patient on pressure controlled ventilation now. Again, patients sit at rate of 20 with 20 centimeter driving pressure, PEEP of 5. And you can see the peak inspiratory flow is 120 and the inspiratory time is 1 second. So we talked about this before, but we would make the patient as an ARDS patient, and as we should notice, the peak inspiratory flow might change a little bit, but the peak expiratory flow definitely will go down. Now let's make him as a COPD patient, and as you can see, the peak inspiratory flow now we're gonna go down, and the peak expiratory flow, this is actually a mistake, will also decrease, so it will be less negative. Let's examine the rate, what happens when the respiratory rate changes. We'll just let it settle down. Let's make him breathe a little bit faster. 33. So here the inspiratory flow went up a little bit, and of course the inspiratory time dropped because this is set I to E ratio. What I want to show is the effect of the patient's muscle effort on the inspiratory flow. So let's go back to a lower rate, and we'll make the patient trigger most of the breath and make him work a little bit harder. So here his patient P mus, or the muscle pressure, is about 5 centimeter. So the inspiratory flow here right now is 120. Let's make him breathe harder a little bit. We're up to 12 centimeter of pressure, and you will notice that the inspiratory flow is going up a little bit. I want to show you the effect on the flow waveform. So here the patient will be breathing really hard, and you can, I think most of us can appreciate this concave here. And just by looking at this sometime on a real patient, just by looking at the flow waveform, you can tell that that patient is working hard without again calculating the PMOS, which needs an esophageal balloon, or the work of breathing or anything. Just by looking this, especially in the pressure support modes when the patient is in weaning, you can tell that he's working hard. Actually, we're trying to work in a formula calculating the mean inspiratory flow, or the area under the curve here of the inspiratory flow, to determine if that could be used as an index of patient passing or failing the weaning. Again, the inspiratory flow here went up to 180, and the inspiratory time is 1.3, again because this is a fixed I to E ratio. And we'll go back to very low effort to, again, so you can notice the difference. It will be nice decelerating waveform here. It's not concave as it used to do before. The flow curves are very important in setting the inspiratory time, especially in the pressure control modes. So in this case, patient is in pressure control, respiratory rate 15, driving pressure 10, PEEP of 5. And if you can notice, his tidal volume is 380, his inspiratory time is 0.8. So how do we set the inspiratory time to get the maximum tidal volume without having to go up on the driving pressure here? Remember, as we mentioned before, tidal volume is basically the flow over time. And if you look at this flow curve here and the time constant we talked about, the inspiratory time constant is not less than 4 times. That's why it's not going to the baseline. So we can improve the tidal volume given to the patient without going up on the driving pressure, just by improving the inspiratory time. So again, this ventilator goes by the inspiratory to expiratory ratio, the I to E ratio. You might be able to do it with fixed inspiratory time. So here we increased the I to E ratio, and we made the inspiratory time, instead of 0.6 seconds, now we are 1.3 seconds. And if you notice, now we have the inspiratory flow almost touching the baseline. Tidal volume was, I think, 370, and we're up to 480. So we gained a lot of tidal volume again without increasing the driving pressure. So what about, can we make him, is increasing the inspiratory time, or the inspiratory flow more than this, would change anything in the inspiratory tidal volume? And the answer is probably no, because once we reach the baseline here, there will be no additional volumes acquired. Rather, you're going to have a longer inspiratory time. You might get, of course, more recruitment. So let's try to go, we'll make it inverse ratio just to emphasize the point. So we'll make him 2.1 2 to 1, and the inspiratory time would be, inspiratory time is now 2.7 seconds. So as you can see, we're just doing a pause here, but the tidal volume has not changed much. Okay, what about volume control modes? If we go here, of course, the volume control modes, the tidal volume will be the same regardless the I to E ratio or the inspiratory time, because the ventilator will give you the tidal volume. What will change is the airway pressure. So this is in a patient, we'll put him on the classic volume control mode with a constant waveform, flow waveform. We'll just make him back to normal 1 to 3 I to E ratio. And of course the patient, because here he is passive, so he's supposed to get the same tidal volume. Okay, the airway pressure right now excuse me, is 17. So let's see what the effect of changing the inspiratory time will do. This time will be on the airway pressure and the flow. All right, so let's go to 1 to 1. Our inspiratory time in the beginning was 1 second, now it's becoming 2 seconds. You should notice that now the inspiratory time is longer, the airway pressure will be less. Even the inspiratory flow here will decrease. Again, the reason is this is because it's a set inspiratory to expiratory ratio, not a fixed flow rate. If it's a fixed flow rate, of course the peak inspiratory flow will still remain the same. Here in this slide we'll talk about the effect of the rise time or the pressure ramp effect on the inspiratory flow and the inspiratory pressure. So if you see here, this is the pressure ramp, and it means how fast is the breath giving or the flow being given. As you can see here, it goes immediately, very fast, so that's why the pressure, airway pressure, looks rectangular, and this is almost like a 90 degrees. But if we decrease it, we have the option to decrease it or increase it. So if we can, let's make it extreme. And as you can see, the breath will be a little bit delayed, and the airway pressure it's not perfect square. And you gotta have to be careful with this because sometimes those can cause asynchronies, and if you're not paying attention why the flow and the airway pressure looks a little bit different, check the inspiratory ramp or the pressure ramp. Sometimes it's under different names for each ventilator. Now we'll talk about something called the expiratory sensitivity. Again, it's under different names, under different ventilators, sometimes called ES. What basically it is, in spontaneous modes, like this patient and pressure support, or in other spontaneous modes, if you look here, it's usually a flow cycle, meaning that when the flow decays down to 25%, the inspiratory phase will stop and exhalation will start. And this is usually by default to 25%, but again, most new ventilator you can decrease it or increase it. So for example, in somebody with COPD and you want them to have prolonged expiratory phase, you want to increase this a little bit, say for example to 40%. What you're trying to really match is the patient muscle diaphragmatic effort, because if this number, say, set very low at 5 in this example, and you can tell the effort here of the patient stopped here, but we're continuing the inspiration for no reason. So you try to match it to the patient's inspiratory effort, and that could be a little bit tricky. But again, it's usually set at 25%. I want you to watch, so this patient's pressure support 15/5. Because of his within normal compliance, about 70 or 75, is getting a tidal volume of 760. Now let's increase this, make it 50%. So now the inspiratory time will be shorter, and that will drop, will affect the tidal volume, because again the inspiratory time constant became less. The inspiration is not reaching down, so you can see the tidal volume dropped. Vice versa, if we made it low, the tidal volume should start going up, but again, this is, you can tell that this is very too much, but the tidal volume will go up and the inspiratory time went up. So again, something to be important to set or look at when you put the patient on a spontaneous breathing mode. We'll mention quickly about the flow volume loop, which we all know from respiratory physiology, which is basically here tidal volume on the x-axis and flow on the y-axis. This is a patient on volume controlled mode, again inspiration and exhalation, and it really gives you an idea of the relation between the tidal volume and the flow. As you can see here in this case, this is a normal compliance patient and resistance, so expiratory flow, let's freeze it here, basically goes down to zero before the next breath, as you can see here. Now we see the difference when we try to make our patient as a COPD with a high compliance and high resistance. Sorry, it will take a couple of seconds until it sets that, but again, keep noticing. So the expiratory flow starting to become short, and you can see the slope is not we're gonna start to be like slow, and you might see the effect of auto-PEEP. Again, it's not totally set the resistance that I set. I set high resistance at 30 and compliance of 100. All right, let's we'll pause it to show the effect of, sorry, it's not letting me catch the auto-PEEP, but you can tell here that the expiratory flow does not reach the baseline before the next breath, so that's another way of detecting auto-PEEP. Now let's quickly make him as a restrictive lung disease, for example ARDS, and we should see that the expiratory flow should start to come down and collapses very quickly. Again, sorry, it will take a couple of seconds. Here, start noticing the expiratory flow will start going down. Here the slope is becoming faster. Expiratory flow is reaching down, as you can see, and will start going. The worse the compliance, actually, this will the expiratory flow will, the lung trying to collapse pretty fast. As you can see here, there will be little pause. So it was interesting to find out that at least this ventilator can actually log multiple loops. You can log the X and the Y axis what you want, and I found that you can log the airway pressure versus the flow. There's no much mentioned in the literature, but from electrical engineering literature, this usually represents resistance. Remember, resistance is airway pressure over flow. So by looking at this, you might actually see the effect of resistance. This is a normal patient, and if we change him again to a COPD patient, you see it start to get more narrow, and that's usually the effect of resistance. Again, its significance is really unknown or unmentioned in the literature, but I thought it might be interesting to see this. Worth mentioning that there is a new ventilator mode called flow controlled ventilation mode. And that's unique. I never seen it, but it's only one ventilator, and it's basically uses a linear inspiratory and expiratory flow, as you can see here, a constant inspiratory flow, and usually the expiratory flow in volume controlled mode are passive, as we talked about, but this one uses a constant or linear expiratory flow in both inspiration and exhalation, and only few studies talk about it that shows some enhancement of lung aeration in the dependent lung regions with some improved gas exchange and decreased lung injury in animal studies. Um, and the authors of those studies claim that might provide a novel option for lung protective ventilation. Again, no much studies or about this new mode, but I just wanted to put it there. So to summarize this talk, sorry if it was a little bit long, I think the flow curves are very important to look at, honestly, more than the pressure or the volume curves. It gives you so much information about the respiratory mechanics, the synchronies with the vent, um, patient muscle effort, and especially in the weaning process. Um, so this is the article that I talked about in the beginning of the talk here. We published in 2020 in the Canadian Journal of Respiratory Therapy, um, called Go with the Flow. At that time it sounded like a catchy, nice name. Now I don't think so. It sounds a little bit silly. Anyway, clinical importance of flow curves during mechanical ventilation. And hopefully it gives you idea and explains everything a little bit more clear. Thank you for watching, and I hope that was helpful a little bit. Thank you.